Now we solved the problem yesterday where we were looking at the use of pressure ratio to come up with the exit temperature, right? Both for the variable specific heat case and the constant specific heat case. Now what we want to do today is to talk about another scenario where we make use of the specific volume ratio instead and solve the problem similarly. All right. So now let's see what we have here. Here we're dealing with air, which is uh, compressed in a car engine from an initial pressure of 95 kilopascal, temperature of 22 degrees Celsius, and it is compressed in a reversible and adiabatic manner. Okay, so whenever you see the words reversible and adiabatic, you should automatically remember that such a process would be an isentropic process, as discussed in the class yesterday. Now, if the compression ratio V1 by V2, this is the ratio of the volumes of the engine, is 8, right? Which means that the initial volume divided by the final volume is equal to 8. We need to determine the final temperature of air in Kelvin, assuming air to be an ideal gas with variable specific heat. So now let's note down what we know and what we need to determine. All right, so we have to determine the final temperature, T2. The system that we're dealing with is a closed system, and it consists of air, which we're going to treat it as an ideal gas with variable specific heat, as specified in the question. At state 1, we have the pressure and temperature given to us, and we have been told that the compression is reversible and adiabatic, which basically means that it is isentropic. Okay. It's an isentropic compression. And we for state 2, the only thing we know is that the volume at state 1 is equal to 8 times the volume at state 2, right? This is something we know from here. And since it's a closed system, the mass at state 1 should exactly be equal to the mass at state 2. Now, all we need is temperature at the exit. And the way we're going to solve this is very similar because now we are having an isentropic process for an ideal gas with variable specific heats, right? So for in all such situations, we can automatically write that the ratios, the pressure ratio P2 by P1 should be equal to the ratio of relative pressures PR2 by PR1. Same way, the ratios of specific volumes V2 by V1 should exactly be equal to the ratio of relative specific volumes VR2 by VR1. All right. Now here we don't have the specific volume, but the volume is given, the volume ratio is given. However, we should remember that for a closed system, because the mass remains constant, M1 is equal to M2, the ratio of volumes will exactly be equal to the ratio of specific volumes, right? Simply because the mass is constant. This will not be true always. This is true only for closed systems. For other systems, it can be true only under special conditions where you're sure that the mass is remaining the same, right, within the control volume. Now, for this particular scenario, it's a very simple situation. We just have to make use of the second formula. And we have V2 by V1 already. That's 1 by 8. We can determine VR1 because the temperature is provided. We just need to get VR2 from there. Okay, so that's how we're going to go ahead. T1, we need to convert to Kelvin to make use of table 822, right? So at 295 Kelvin, the VR1 is 647.9. So now we make use of the relationship between specific volumes and relative specific volume ratios for an ideal gas undergoing an isentropic process with variable specific heat, which is exactly this equation right here, or this equation right here, which I wrote. Now the ratio V2 by V1 is already given. That's 1 by 8. VR1 we determined 647.9. So VR2 would be 80.99. Now we need to remember that this value corresponds to a given temperature, which is T2, right? It will not correspond to two temperatures. It corresponds to only one temperature because VR depends only on only on temperature and nothing else, right? So you can go to the ideal gas table back again and solve for it, and you'll need some interpolation, and you'll get T2 to be 662.7, right? So this is the temperature at the exit that we wanted to determine, and all we had to do was to apply the isentropic process formula for an ideal gas with variable specific heat, right? That's how we would solve this. Now let's move forward and talk about how we look at isentropic efficiencies of various steady flow devices. Now we already spoke about the isentropic processes earlier, and we said that the isentropic processes tend to be the most ideal processes for adiabatic devices in general, or for steady state, steady flow um, devices, right? Like the turbines, compressors, nozzle, diffusers, and so on and so forth. Now, the key point about isentropic process, as we discussed before, is that it involves no irreversibilities, meaning the process is reversible or at least internally reversible. Okay. And second thing it needs to satisfy is that it needs to be adiabatic. So if you're dealing with any adiabatic device, you cannot automatically say that if it's adiabatic, it should be isentropic. No, adiabatic by itself does not mean isentropic. If you're having an adiabatic device already, then if the process is reversible or internally reversible, then you can say such a process is also isentropic, right? Now, in terms of the isentropic turbine efficiency, as we already mentioned, if a turbine, if any substance undergoes an isentropic expansion within the turbine, it's going to give us the maximum possible work output for the given set of pressures that we are considering, right? So it's important, really important to remember that we are fixing P1 and P2, right? P1 and P2 are fixed for both. They're fixed and they are the same for both the actual scenario where you have irreversibilities and the ideal scenario where you don't have any irreversibilities and when the process is completely reversible. So we are starting at state one at P1 and T1 is fixed. No question about that. The pressure at which we are going to reach is also fixed. This is a constant pressure line, as you see here. The only question is where exactly is state 2. If the process is isentropic, it moves along the straight vertical line, ends up at state 2s, right? 2s indicating it's an isentropic process. If there are some irreversibilities, then from our entropy balance equation, we know that whenever you have irreversibilities in a steady state, steady flow device like a turbine or a compressor, right? S2 will be greater than S1, right? Entropy at the exit will be greater than entropy at the inlet. So you have the exit point can be anywhere on this line, right? Anywhere on the constant pressure line, but it should be to the right of 2s. The entropy at 2 should be greater than the entropy at 2s, or entropy at 2 should be greater than entropy of 1, right? And therefore, when you draw then the process line for any actual process where there is irreversibility happening, right, it'll appear somewhere on this line. And here we have the point 2 appearing right here. And when you look at the difference in enthalpies, you can very clearly see that if the process was isentropic, meaning if the isentropy was constant during the expansion between a given value of P1 and P2, then the difference H1 minus H2S would be larger. If there is an entropy increase, then the difference becomes smaller. And this difference becomes smaller and smaller as S2 becomes larger and larger compared to S1, right? So higher the entropy generation, in other words, higher the entropy generation within the expansion process, the lower would be the difference between H1 and H2, and eventually the lower would be the work output. So here, when we are looking at it, the isentropic efficiency of the turbine is defined as the actual work output, which is H1 minus H2, actual work output per unit mass, divided by the isentropic work output, which is H1 minus H2S, right? And again, to reiterate the point, this is happening because S2 is greater than S1 for a process which is irreversible. Okay. So what are these values in reality then? Well, for most parts, the isentropic efficiency is somewhere in the range of, let's say, 70 to 90%, right? This is the typical value for a turbine, and we can expect the values to the higher end of the values to be achievable or to have been achieved recently in the recent past. Like earlier, if you go back 20, 30 years, it started off with efficiency of 0.7, okay, or 70% isentropic efficiency. Now let's move on to other devices, right? So let's move on and talk about the isentropic efficiency for a compressor, or let's say a pump, right? Here, as we know, a compressor or a pump, its role is to increase the pressure of any fluid that comes in, and it does so by taking in some work input. Okay, so this is important. Again, just like we said in the turbine, the initial and the final pressures, or the inlet and the exit pressures, are fixed. Okay, for both reversible and irreversible processes. Right now, here, if the process was isentropic, then the work input would be minimum. For isentropic compression process, work input would be minimum. Okay, so this is really important. Uh, However, if the process is not isentropic, if there are some irreversibilities involved, of course, the work input will be higher. So it's very easy to look at this. Again, we said state one is fixed. The entry point to a turbine, a compressor or a pump is fixed. Okay. If and of course the pressure P2 is also fixed. Now, if it is undergoing isentropic compression, then you have a straight vertical line going all the way from 1 to 2s, and the work input per unit mass would be S2s minus S1. All right. So as we see here. Now, on the other hand, if there is some entropy, which will always, if there's some entropy generation happening during the process, which means that S2 is greater than S1, then in all such cases, the only accessible states are to the right of this point 2s, as shown here. And as we need to stay on the same pressure line, it's going to be somewhere on this line. If it's somewhere here, as shown in this picture, we can see that the enthalpy difference increases. S2 minus S1 is larger. So which basically means that for increasing the pressure by exact same amount, we need to provide more work input. All right. And since the efficiency formula is designed to ensure that the efficiency value is always below 100%, we switch the formula here for a compressor and write it as isentropic work input divided by the actual work input. Okay, so it's important to know that there is difference in the isentropic efficiency formula when you're dealing with a compressor or a turbine. Okay, so it's really important to know this difference. Again, when we're dealing with a compressor, of course, when we talk about a compressor, it's mainly used for compressing gases, right, or things which are in the superheated vapor state. The efficiency is roughly again in the 75 to 85% range, slightly less than that for a turbine, but it's still very reasonable. And of course, as technology advances, we are achieving higher and higher values for the efficiency, but it's still around 85. Let's say it's still slightly lower than the value for a turbine. Now, if you're dealing with a pump, right? Remember, a pump is something that deals with incompressible substances. Pump is something that is used to increase the pressure of liquids, which are incompressible substances. Okay, so for a pump, we can also write the isentropic efficiency formula, of course, in terms of enthalpy, just like we wrote for a compressor, but we can further note down the H2S minus H1, or the work input per unit mass for a pump, as specific volume times delta P. Right now, we will look a bit into. We'll spend some time looking at where do we get this work input formula from, or reversible work input formula from. But for now, let us just take it as it is and say that, okay, if it's a pump in incompressible substances, where if you're using a pump to compress a liquid, let's say, which is an incompressible substance, meaning specific volume is constant, then V delta P, or V times P2 minus P1, is going to give us the pump work input for an isentropic process. All right. Now, the efficiencies for pump varies quite a lot, but it's somewhere again in the range that you see for the compressor. Okay, it depends on size, design, and other factors. Now, if we cool compressor intensely, or we cool compressor between multiple stages, then what we need to use is isothermal efficiency, right? And the isothermal efficiency formula is slightly different, and it's shown up here. Now, again, you do not have to remember the isentropic efficiency formula, the isothermal efficiency formula for a compressor. We will be using isentropic compressor efficiency almost always, right? So this is something that you should know for sure. This one is additional knowledge, all right? Okay, so now let's talk about nozzles, right? So again, in this nozzle, we're dealing with more or less this a similar thing, meaning the inlet state is fixed and the outlet pressure is fixed. The exit pressure is fixed. So P1 and P2 are again fixed, and they are same for both actual processes and isentropic processes. Okay. Now the isentropic nozzle efficiency is defined as the ratio of actual isentropic nozzle exit specific kinetic energy. Sorry, it's defined as the ratio of actual uh, nozzle exit specific kinetic energy, which is this part right here, divided by the isentropic nozzle exit specific kinetic energy. Okay. Now these can be confusing. So let's look at what we're saying here. We're simply saying that you have a nozzle. The role of a nozzle is to increase the velocity. We have V1 and V2. We know that the whole purpose why we build a nozzle is because we want V2 to be greater than V1, in fact, much greater than V1. And we are able to achieve this by decreasing the pressure. Okay, P2 is smaller than P1. Now, the point is V1 is usually really, really small. Okay, so we only focus on V2 because that's our target. So in terms of nozzle efficiency, we basically define it as the kinetic energy or the specific kinetic energy at the exit, meaning V2, right? V2 squared by 2. So this is kinetic energy divided by mass, right? This is specific kinetic energy. The value that you get for the actual situation divided by the value that you get for an isentropic situation, okay, where the velocity could be different. In fact, velocity is higher, right? V2s squared by 2. So this is what you see here, V2 squared by 2, the exit specific actual kinetic energy divided by V2 squared by 2 for the isentropic case. All right. Again, this is specific kinetic energy and it's at the exit. Okay. Now, if the inlet velocity at the fluid is small to the exit velocity, which is almost always the case, unless you have been provided the inlet velocity also, right? In all such cases, we can simplify the energy balance for a nozzle to be written as H1 is equal to H2A plus V2A squared by 2. How do we get this? Well, the normal equation for a nozzle is H1 plus V1 squared by 2 is H2 plus V2 squared by 2. Okay. Now we're saying V1 squared is almost 0. So that's when we can say H1 is equal to H2A plus V2A squared by 2, right? A simply stands for actual, okay, the actual process. Now, once you have that, then you can define the isentropic efficiency as H1 minus H2A, right? Which is because we are simply looking at the ratio of specific kinetic energies at the exit. So it's going to be equal to H1 minus H2A divided by H1 minus H2S. Okay. And again, when you look at it, if the process what's in the nozzle is isentropic, right? It goes along a straight vertical line. The difference between these two, H1 minus H2S, is actually larger. Okay, which basically means that V2S squared by 2 will be larger. On the other hand, if there is irreversibility in the process, then the point 2 has to be to the right of point 2s, which means that the difference in the enthalpies here between 1 and 2a is going to be smaller, which essentially means that V2A square will be smaller. So essentially what's happening is if you have an isentropic process, you get the maximum possible velocity in the nozzle for a given value of P1 and P2. Okay, so this is really important to remember. P1, P2 remains the same, whether the process is actual or isentropic, right? Now, but when you have irreversibilities, of course, then what happens is that the temperature at the exit is slightly higher and you will have lower velocities. So this is the actual velocity for a particular scenario, and 666 is the isentropic velocity. And as you can see, the isentropic velocity has to be greater than the actual velocity. Okay, and this is basically how the nozzle efficiency is defined. So now we will solve a couple of problems to understand how this all works. And before we go there, just a small information to add. The efficiencies for nozzles are extremely high, right? Typically higher than 95%. They are also approaching 98%. So this is something where we don't lose a lot due to irreversibilities, right? So it's time ahead. It's time for us to now move ahead and start solving problems. All right, let's start with this problem here. We are dealing with a steam turbine, okay, and the conditions are provided to us at the inlet, right? So let us note down everything. So we're dealing with a steam turbine, okay. This diagram will be provided to you. At the inlet, the conditions are 5 bar at 320 degrees Celsius. Of course, it's a steady state, steady flow device, and we have been told that the exit pressure or the steam leaves the turbine at a pressure of 1 bar. So P2 is 1 bar. It's a steady state, steady flow device. So mass flow rate at the inlet should be equal to mass flow rate at the exit. Okay, m dot n is equal to m dot out. And turbines are always steady state, steady flow devices. So that's not something that you need to worry about. But the questions will usually mention that it's operating at a steady state. Now, it also says that there is no significant heat transfer between the turbine and the surroundings, right? Which basically means that the expansion process in the turbine is adiabatic. There's no heat transfer. Okay, Q dot is 0. And the kinetic and the potential energy changes between the inlet and the exit are negligible. Okay, that's the usual stuff that we do. Now, here it says that the isentropic efficiency is 75%. If the isentropic efficiency of the turbine is 75%, we need to calculate the work developed per unit mass of the steam which is flowing through the turbine. So we need to calculate the specific work output of the turbine, right? So we're dealing with this open system, one in, one out, and it's steam. Okay. So let us note down what is provided to us, right? So what is provided to us is the isentropic efficiency for a turbine. And from the formula that we remember, we said it's equal to the ratio of the actual work output, which would simply be H1 minus H2A or H1 minus H2 divided by the isentropic work output, which would be H1 minus H2S. Okay. Now we have enough information on state 1, right? So we can actually go ahead and determine H1 from the property table. We do not know H2 at all. H2 is not known to us, right? But the isentropic efficiency is provided, and it said that it's equal to 75% or 0.75. So from here, the easiest way to go ahead with solving this is that what we need to do is we need to somehow find H2S. Okay, so the question is, can we find H2S? Okay, H2S is the enthalpy at the exit for an isentropic process. We have the pressure at the exit already available to us, so all we need is one more property, okay, to fix state 2S. And the key part here is we know that for an isentropic process, S1 is equal to S2S, right? S1 is equal to S2, right? Or S2S, just to say that it's an isentropic process. Now, for state 2S, the entropy is known to us, and pressure P2 is going to be equal to P2S. It's going to be 1 bar. So now we have the pressure and we have the entropy. Using this, we can basically get S2S. Okay. Now, once you have S2S, it's a very straightforward formula that we're looking for. What we need is basically the work output per unit mass, so which is basically H1 minus H2, right? So isentropic efficiency can also be written as the actual work output, ACT, divided by the isentropic work output, which is H1 minus H2S. Okay. Now I have H1, I have H2S. I'm going to substitute that into here, and the work output, the actual work output, is simply going to be equal to 0.75 times H1 minus H2S. And when you plug in those numbers, you get the actual work output. Okay? It's as simple as that. The only thing you got to recall is that you got to remember that for an isentropic process, entropies remain same, and you have to make use of that. Okay, so this is what we want to determine, and you say it's equal to simply isentropic efficiency times H1 minus H2S. We can get H1 directly because it's superheated vapor, pressure, temperature given. From here, we will also determine S1 because this is exactly equal to S2S. Okay, and then S2S can be determined because we know pressure P2 and S2S. So here we can get S2S, and using these two, simply we can get the work output of the turbine. So it's really, really important to remember that P2 is equal to P2S, as we discussed before. The pressure at the exit does not change whether the process is reversible or irreversible. Okay. So, and the other thing is a process being adiabatic is not enough to make it isentropic. So all adiabatic processes are not isentropic processes. So it's important to remember this. Okay. So now let's go ahead and solve one more problem. Here, let's deal with the compressor. Okay. So here we have been told that we have a compressor which is taking in refrigerant R22, and it enters the compressor at -5 degrees Celsius, 3.5 bar as provided. And this is compressed adiabatically. So again, we're dealing with adiabatic compression. Okay, and it is compressed adiabatically to 75 degrees Celsius and 14 bar. Then the mass flow rate is also provided, 0.07 kilogram per second. We know that it's a steady state, steady flow system because it says steady state here. Otherwise, without that also, we know that compressors are always steady state, steady flow systems. So we can say M2 is equal to M.2 is equal to M.1 is equal to M dot, right? That's the mass that comes in should be equal to the one that goes out. The usual suspects, the kinetic and the potential energy changes, we can neglect them. And for this condition, we need to do two things. We need to first determine compressor power, and second, we need to determine the isentropic efficiency of the compressor. So this is again a very straightforward problem. Okay, so compressor power, as we have seen before, is simply equal to mass flow rate times H2 minus H1. Okay, now the question is, do we have H2 and H1? Well, the states are exactly provided to us. Okay, we know the what is state 2. We know because pressure and temperature are given. Same way pressure and temperature are given at the inlet, so we know what is the H1, right? So we can get these values directly from the property table. M dot is already given in the question, so this is very easy to determine. The question is, how do you get the isentropic efficiency? Now, isentropic efficiency for a compressor, as we discussed before, is simply a ratio of isentropic work input, which would be S2S minus H1 divided by the actual work input, which would be S2 minus H1. Okay, so I'm canceling out M dot from both numerator and denominator. Now we already have this part right here. Okay, we have S2 and H1. We can get this part. So of course we have H1, so H1 is already known. The only part is S2S. So the question is, how do you determine S2S? Well, the answer to this is again is very simple. For S2S or for state 2S, you need two independent intensive properties, right? So one is the pressure, of course. We said P2 is equal to P2S is equal to 14 bar. The other property is that for state 2S, the entropy is going to remain constant. It's an isentropic process. Okay. It's an isentropic compression process for state 2S, and therefore entropy at state 1 will equal to the entropy at state 2S. Now we have enough information at state 1 to get the entropy at state 1. So from here we're going to find S2S, and using this pressure and entropy, just like we did in the previous example, we're going to get S2S. Once you get S2S, then it's simply a matter of plugging into this and getting the isentropic efficiency. Now it's really important to remember that S2S, or the enthalpy for the isentropic state, is always going to be smaller than the enthalpy for an actual compression or expansion, right? For an irreversible process. So this is one very useful hint that can help you in calculations, and that can help you do a quick sanity check whether to understand what you're doing is correct or not. All right, so here we start again. This is simply what we need to do. H1 you can get from the table. Same way H1, H2 also you can get from the table because pressures and temperatures are provided, and it's superheated vapor state that we're looking out for. Okay, so you plug in the numbers, and 3.11 kilowatt is simply the work input into the compressor. Now for isentropic efficiency, as we said, the only part we need is S2S, and we get it by finding S1, which is equal to S2S, one property, the other property being the pressure itself. Using these two, we can find H2S, and it comes out to be 285.58. You plug in those numbers here, 285.58, 249, 294.17, 249.75. S2, S minus H1, S2 minus H1. As again, we can see here, S2S is smaller than S2, just like we expected. And when you put in these numbers, the efficiency comes out to be 0.81 or 81%. Okay, so this is a very simple way to show how this problem works, and it's rather simple, and it's very easy to understand. And I want you to practice this to make sure that you understand and know how to deal with it. There's actually not much to it, right? It's a very, very simple problem. So now let's go ahead and solve one more problem just to complete the set of isentropic efficiencies. We did one problem on turbine, one on compressor. So now let's do one on nozzle also, and complete the entire set of problems. Okay, so here what we're dealing with is a nozzle, right? And again, let's note down the stuff that we have. So the question says that the air is being it's accelerated in a 90% efficient adiabatic nozzle. So the isentropic efficiency is already given. It's 90% or 0.9, and it's going from a low velocity to 240 meter per second. Okay, so it's going from some low velocity, we don't know what that is, to 240 meter per second. So V2 is 240 meter per second. Okay. V1, if it's not provided, you can easily take it as 0 meter per second, right? You can just neglect it. Okay. Now the pressure and temperature at the inlet is given. It's 400 kilopascal and 820 Kelvin. Now we need to make some assumptions. We can assume air to be an ideal gas with variable specific heat. So variable specific heat is important here. And making this assumption, we need to actually calculate the exit temperature and the pressure for air. So we need to calculate the exit temperature T2A, or the actual exit temperature, and the exit pressure, right? So P2, as we said before, is the same for both actual process as well as the reversible process. Okay, so now let's focus on getting the temperature first. Now we can simply look at the energy balance equation for the nozzle. So we know that for a nozzle, we can write the energy balance equation as m dot h1 plus v1 square by 2 should be equal to m dot h2 plus v2 square by 2. We know that m dot 1 is equal to m dot 2. So basically, h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. V1 is almost 0. It's not provided in the question, and it's usually very, very small compared to V2. So if it's not given in the question, you can approximate it to be 0. What we have been provided is V2. Okay, and also we have enough information to get enthalpy as stable. Ideal gas, you have temperature, you can get enthalpy directly. So all that we need from here is basically S2. So basically H2 can be written as H1 minus V2 square by 2. Remember, when you're plugging in the numbers, you got to divide this by 1000 to convert the velocity to the velocity square by 2 to kilojoule per kilogram. Okay, so enthalpy can be easily obtained from table 822. You plug in the 240 square in here, and you can get the enthalpy as state 2. Once you have enthalpy as state 2, obviously it directly relates to a certain temperature, and we will be able to get the actual temperature T2. The reason we can get the actual temperature is because we have been provided the actual velocity at the exit. Okay, remember, if this was an isentropic process, the velocity V2S would actually be greater than V2A. So V2S, you can expect it to be greater than 240 meter per second. Right. So this is the first part of the problem. This is how you would determine the temperature. Okay, and it's shown here again. At T1, you can get H1 directly. We will also get PR1 because we need it later. And S2 is simply equal to H1 minus V2 square by 2. We know that V1 square is 0, or V1 is 0. And when you plug in the numbers, be careful to remember to divide by 1000 to make the correct unit conversion. You can get H2 to be 815.18 kilojoule per kilogram, which through interpolation means that its T2A is 793.8 Kelvin or 794 Kelvin. Okay, so this is part A of the problem. All right, so now let's look at the second part of the problem, P2. Right, we need to find the pressure at the exit. Now we have discussed it several times that for all these isentropic processes, the pressures P1 and P2 are fixed. So P2 is exactly equal to P2S, right? And we have a formula relating the ratios of pressures in an isentropic process to the ratio of relative pressures, right? So we can say that P2 by P1 will be equal to PR2 by PR1. But we got to remember that these temperatures right here, these are the temperatures that correspond to an isentropic process. PR1 would certainly depend on T1, but PR2 depends on T2S. It is PR2 does not depend on T2A, and what we have here is T2A. Okay, we should know that T2A is going to be greater than T2S, and this, strictly speaking, applies only to an isentropic process. And we are able to use this for finding the pressures at the exit simply because P2 is going to be equal to P2S. Okay, but T2A is not exactly equal to T2S. So the first point is we need to actually get T2S. Okay, how do we get it? Well, we can get it directly by making use of the efficiency of the nozzle, right? And then sort of obtaining the enthalpy and then the temperature from there. Or another way is, instead of getting the temperatures, all what we can do is we can get the enthalpy, and for that enthalpy, S2S, we can get the corresponding value of PR2. Okay, so that's what we're going to do here. So this is the key equation that we're going to make use of it, but we know that this works for isentropic process. So this PR2 corresponds to temperature for an isentropic process, right? And that is something that we got to be very careful about. So we're going to rely on the isentropic efficiency of the nozzle to obtain the uh, the temperature for an isentropic process, or let's say the enthalpy for an isentropic process. So it's going to be equal to H2A minus H1, the actual decrease in the actual change in enthalpy divided by the isentropic change in enthalpy, right? So there's basically going to be an increase in enthalpy from H1 to H2. So we have H2A because we have T2A. We have H1 because we have T1 already. From here we get H2S, right? So when you plug in the numbers, H2S comes out to be 811.98 or 812. Now you have two options from H2S. You can go and get T2S and then go to PR2. Okay, it's your choice. It's not necessary, but some people want to go step by step. You can do that. Otherwise, we know that enthalpy and pressure, they depend only on temperature. So for a given value of enthalpy, there should be only one value of PR. This works only for ideal gases, right? Not for anything else. So therefore, from directly enthalpy, you can go to PR2, and for enthalpy of 811.98, it corresponds to a relative pressure of 45.75. Okay, so now I can put this number into the equation, and PR2 by PR1. PR1 I obtained at T1 times P1, the pressure at the inlet, 400, is going to give me the pressure at the exit, 348 kilopascal. Now this would be exactly the same pressure if the process was isentropic. Okay, so P2S is equal to P2 as 348 kilopascal. The only difference would be for an isentropic process, the temperatures would be lower. Okay, so T2S would be smaller than T2A, and the velocities for an isentropic process would be greater than the velocity for the actual process.